questions here? This should be familiar, right? Yes. Okay, so that's a good question. Why are we talking about a delta B? And that's exactly what I'm going to talk about now. Okay, it's a delta B, not so much a change, but think of it as a little piece. Much like when we were breaking up charge distributions into pieces, we had a delta E, and then we added all those deltas together and got a total electric field. We're going to be doing the same thing now with the current, with the magnetic field, because this is one segment of the wire, right? But there's another segment of the wire here and another segment of the wire here. And we want to find the total magnetic field due to all of those segments. So we're going to need to sum up all of those delta B's. Okay. So this formula on its own isn't terribly useful because it's only applying to a small little piece of a much larger current distribution. But what it's useful for is for then adding up all those pieces and getting the total magnetic field of a current distribution. Okay. So let's actually try that. Let's actually try that for a very long wire and see if we can calculate the magnetic field of a very long wire. Let's, as usual, we could do this analytically or we could do it numerically. And let me show you what the numeric simulation looks like first. We have a long straight wire. Okay, so this is just a metal wire and it's got a conventional current running to the right, okay? And I want to find the pattern of magnetic field at various locations surrounding this wire, okay? So I'm going to break it up into pieces. I have the Biot-Savart law, which tells me the magnetic field due to each individual piece of a length delta L, or dl as it's written here. And I've got an R vector that points to some observation location here, okay? So everybody, what's going to be the direction of the magnetic field due to this piece at the top? Fingers in the direction of delta L. Curl them up towards R hat, right? Thumb points out, okay? If I move to the next piece, that delta B direction should be the same, right? If I move to a piece way down here, that delta B direction should be, or the same, right? Because delta L is that way and R curls all the way back, but it's still pointing, has a component upward. So when I do that, for the first couple of segments, you can barely see anything. But as we start to get closer, and let me see if I can zoom in here a little bit, particularly right there. Okay, that segment, why does that segment make a big magnetic field but the other ones did not? It's close, right? And so we still have this 1 over the distance squared dependence. So the closer we get, the bigger the delta B. And we're just keeping sort of a running total of the total magnetic field here. And so we get another segment that contributes a large delta B. And then the rest, you can see slight changes, but not much change because the rest are contributing essentially 0 as we get farther away and as that angle gets larger, right? Because we can also write a cross product as, if I say the magnitude of delta B, I can say it's mu naught over 4 pi I times the magnitude of delta L times the magnitude of R hat times the sine of the angle between them. Okay, just looking at the magnitude there. If the angle is, that angle is almost 180 degrees, and sine of 180 degrees is what? 0, right? Sine of something close to 180 is approaching 0. So this is not only far away, but the cross product is giving us hardly anything. Okay, so let's just see what we've got. So we did all those I delta L cross B's, and if I'm looking at it this way, we did in fact get a magnetic field perpendicular to both the direction of R and the direction of delta L. We're now moving to another observation location, and our observation location now is at the same X and Y position, but it's on, or same X position, but a different Y and Z position. It's going to be on sort of on a circle as we go. We're going to have a series of observation locations around a circle surrounding this this wire. So we do that, okay, and we get a magnetic field at that location. Just, again, adding up all those delta B's. And we keep on doing this at different locations. And I can just shift the perspective here just to show you how we are getting this curly-looking pattern, which kind of looks like we had, if you remember last week, we showed the single proton moving, and the magnetic field had this curling pattern. The proton's field changed, and well, we speed it up here just to move things along. But if this is a steady current, then these magnetic fields here are actually staying constant in time. And so we get this nice looking picture where the conventional current, from this point of view, the conventional current's coming out towards us, and you get this pattern of magnetic field where it kind of curls around. And this is another way of doing the right-hand rule, which you may have seen last time, and you can tell me if you did. Did you see this rule last time? Okay, you didn't talk about this. Okay, so let's talk about this. Two ways of getting the direction of the magnetic field. We can either do the cross product right-hand rule, which says point your fingers in the direction of delta L, basically the direction of conventional current. Curl the fingers like any cross product towards the second vector, which is the r hat direction, and your thumb gives you the direction of the magnetic field. Well, another way you can do it, and it's up to you which one you want to use. Sometimes it's more useful to use one than the other. But note the pattern here. If I have my thumb pointing in the direction of conventional current, which is out towards us, if I wrap my fingers around it, my fingers are curling around in the same direction that the magnetic field is curling around the wire. So I could also do the right-hand rule this way. Point your thumb in the direction of conventional current. It's got to be conventional current. Fingers curl around in the direction of the magnetic field. And then to get the magnetic field at a particular location, it's where your fingertips are and how they're pointing, right? So if I have my, go back to here, if I have my fingertips at the top, they're pointing to the left. If I curl my fingertips all the way around to the bottom, they're pointing to the right. Okay, so your fingertips essentially give you the observation location that you're interested in. Okay. Questions here? Okay, let's try, we're going to do this analytically as well and work out a solution to this. But let's try a couple of questions before we do that. Okay, let's start with a simple one. Here's the direction. Okay, here's the this little X position, this little location is in the same plane as the screen and the wire. This arrow is the direction of electron current. This is the direction of little I in this picture. What's the direction of the magnetic field at that observation location? Okay, so most of us are saying answer 6, which is the negative z direction. Be careful of the sign. This is the direction of electron current, not conventional current, right? The direction of conventional current is the other way. Okay, so two ways to do it. You can either say I is that way. R is pointing from the source to the observation location, so I, delta L, cross R, thumb points in, right? Or you can point your thumb in the direction of conventional current, and then my fingers, when they reach down here, are curling into the page, so that's the negative z direction, right? Are we okay? Or you can think about what are the electrons actually doing. We would have an electron moving in that direction. V cross R hat is out, but you have to flip it because you're multiplying by a charge which is negative. Okay, so that would also, so no matter how you slice it, it's got to give you a magnetic field pointing into the board. Okay? Everybody okay there? Let's try another one. Okay, now these arrows are conventional current. These arrows are conventional current. So, but we have two wires, two in parallel. Okay, same currents, same distance away from the observation location. The observation location is right in the middle. What is the direction of the net magnetic field? And still not unanimous. Let's see what we said. We said big vote for answer 7, which is 0, and a big vote for answer 5, positive Z. Well, magnetic fields obey superposition, just like electric fields. You add them up as vectors to get a net magnetic field. So we can find the magnetic field of the top wire and the magnetic field of the bottom wire. For the top wire, we have capital I going that way. And here's the observation location. Again, take your pick. You can either say I delta L cross R, which points downward. Just pick a segment in there. They're all going to be the same direction. I delta L cross R hat, thumb points out due to wire at the top. We'll call this 1. This is B1. Wire at the bottom. I's capitalized that way. R's that way. Fingers in the direction of capital I. Curl them towards the observation location. Thumb points out. Yep. So when I add those two together, I'm going to get a net magnetic field that points out. Other way you can think about it, if I put my thumb in the direction of capital I have to imagine curling my fingers all the way behind the wire until my fingertips reach the other side, because that's where my observation location is, right? If I wrap my fingers all the way around, when they reach that point, the fingertips are pointing out, right? If I do the same here, I, pointing in the direction of my thumb, curl my fingers all the way around until I wrap them around the wire, and they're pointing out when they reach that side. Okay, so both are going to give me a magnetic field in the same direction. If one of those was flipped, what would be the answer? 0, right? If they were both in the same direction, currents in the same direction, they would be 0.